Hello and welcome to Controllers Tech. Today I am going to cover a very interesting LCD display. In the past we have covered LCD-1602 displays in parallel mode, and also via the I2C, where we connect the PCF8574 module at the back of the display. In the parallel mode, we need to connect at least 10 pins from the MCU, which includes 4 data pins, 3 control pins, and rest for the power. This issue of connecting a lot of pins is solved by soldering an I2C converter module at the back of the display. It reduces the pins from 10 to 4, but the entire setup design becomes bulky. Today I have a very interesting display. It is LCD-1602, but it comes within Built-in I2C mode. So we have only 4 pins for the connection, and the design footprint is that of a normal LCD-1602 display. You can see the display, and the pins in the picture. There are only 4 pins: VCC, ground, clock, and data. This is how the display looks at the back. We only have 4 pins available to connect to the MCU. The pins have the pitch of 2 mm, therefore I have soldered the wires directly to the pins, instead of connecting a header. I am connecting the display to the Nucleo F446RE. The clock pin from the Nucleo connects to pin number 3 on the display. The data pin from the Nucleo connects to pin number 4. The pin number 2 is the ground pin, so connect it with the ground of the Nucleo. The display can be powered with 5 volts, or 3.3 volts. I am using the 3.3 volts here. You can see the display is powered up. Here you can see the string being displayed on it. This is from my test project. This one is black pixel color with white background. You can purchase it from AliExpress, and if you are watching from India, you can purchase it from controllerstech.store. The display is available in white background, and in yellow background. Today in this tutorial we will cover how to interface this display with STM32. Although we can use the same old LCD-1602 I2C library with it, but we still need to modify that library a little. So let's start the Cube IDE, and create a new project. I am using F446RE. Let's give some name to the project, and click Finish. I will set up the clock first. Here I am bypassing the external clock source, so that it can use the crystal from the ST-Link. The board has 8 MHz crystal on it, and we will run the system at maximum 180 MHz clock. Alright, let's enable the I2C now. I am going to remap the I2C pins, so that it can be set as per the connection made earlier. The I2C is in the standard mode, with the clock speed at 100 kHz. That is all the configuration we need to do. Click Save to generate the project. As I mentioned earlier, we can use the I2C-LCD library that we have used in a lot of projects before. Here I have the library files for the I2C-LCD. Let's copy the C file in the source directory, and header file in the include directory. Let me change this inclusion to main.h, so that it remains flexible throughout different MCU series. We used these functions in previous LCD videos, and we will use them today also. Before we modify the library source file, let's take a look at the display datasheet. The LCD-1602 module used in this tutorial uses the AIP31068 driver. This driver uses the I2C and SPI interface to connect to the display. Though I have the I2C model with me, so I will focus on that part. Let's just skip everything, and jump to the main part. Here is the I2C interface protocol shown in the picture. Let's check the slave address first. We know that the whole library uses the 8-bit slave address, so we need to consider the read-write bit also. The slave address is 00111110. This makes up 7C in hexadecimal. Let's define the slave address in the library. Now to send the data or command to the display, we need to use the 16-bit command word. This command word consists of a control byte and a data byte. The most significant bit, CO, is set to 1, if there are more control bytes following the current data byte. But we will send one command byte or one data byte at a time, so the CO bit will be 0. So let's focus on this part, where the CO bit is 0. The control byte is now just used to configure the RS bit. When we send the command, the RS bit will be kept 0, and while sending the data, this bit will be set to 1. Let's modify the I2C LCD source file according to this method. The LCD send command function takes the 8-bit command as the parameter. Let me delete the previously written code first. Let's define a 16-bit command word. Since this is a command, the RS bit in the control byte will be 0, and hence we will simply copy the command byte. Now we have our 16-bit command word ready to be sent to the display. But the I2C bus is 8-bit in size, and hence we need to send the 16-bit command word as 2 different bytes. First we will send the control byte, followed by the data byte. Let's define an array to store 2 bytes. We will store the control byte first, so shift the command word to the right by 8-bit. Then store the command byte at the next position in the array. The data has been stored, so send it via the I2C. The slave address is already defined above. We will send the command array, 2 bytes in total. That is all we need to send the command to the display. Now let's see the LCD send data function. The function takes the data byte as the parameter. Define a 16-bit variable, data word. Since we are sending the data, the RS bit needs to be set to 1. So we will set a 1 to the 14th position, and then add the data to it. We will send the 16-bit data word as 2 different bytes. First we will send the control byte, followed by the data byte. Let's define an array to store 2 bytes. We will store the control byte first, and then store the data byte. The data has been stored, so send it via the I2C. That is all we need to do in order to send the data byte to the LCD. Let me write a proper method to clear the LCD. Here we will simply send the command 1 hex to the LCD, then wait for a few milliseconds for the command to process. The initialization sequence of this LCD is smaller than what we have used in the previous one. Here you can see, we just need to wait for a few milliseconds, and then directly send the function set, display control, and other commands. So we don't need all this part. Actually this was used to initialize the LCD in 4-bit mode, but this particular LCD is by default used in the 8-bit mode. Even if we leave this as it is, it won't have any effect on the LCD. Here the commands are set as per the instruction given in the datasheet. The comments in front shows what configuration is being used for each command type. You can read more about these functions in the instruction table. For example, the n bit in the function set controls whether we are using 2 lines or 1 line. The f bit controls the font type. Here you can see when the n bit is high, the display is set to use 2 lines. Also when the f bit low, the 5x8 dot format is used. This makes the function set common equal to 28 hex. This is being used here. You can check the other commands as well, and modify them as per the need. Now let's open the main file. Here we will first include the library header file. Now in the main function, initialize the LCD. We will put the cursor at the beginning of the first row, and send a number string to the display. Then put the cursor at the beginning of the second row, and send an alphabetical string. Let's build the project. We don't have any errors, so let's flash it to the board. Here you can see the strings are being displayed at their respective positions. So the display works just fine. I found this one even better than the other LCD1602 with an attached PCF module. The response of this display is way better than the other one. Now let's display some numbers on the LCD. This could be useful if you want to display some sensor's value, or voltage levels. Let's define a 16-bit number that we want to display on the LCD. We need to define an array to store 5 characters. This is because we are going to convert the 4 digits, so the array should be able to store them in the character format. Here in the main function, after displaying the strings, let's wait for 2 seconds, and then clear the LCD. Now we will use the sprintf function to convert the number to the character format, and store it in the array we defined. Now let's put the cursor at the 5th column in the top row, and send the array to the LCD. We need to include the standard I/O header file for the sprintf to work. There are still some warnings because the sprintf takes the character pointer as the parameter. So let's typecast the array to the character pointer. Alright, let's build and flash the code to the board. You can see the number is being displayed at the requested position. So the display works fine by modifying the previously written I2C-LCD library. This is it for the video. I hope you understood the working of this AIP31068 based LCD display. The Indian viewers can purchase it from controllerstech.store. That is it for today. You can download the code from the link in the description. Leave comments in case of any doubt. Keep watching, and have a nice day ahead.